ready? Here's the second one. Okay, so this is the same problem, okay? We're just doing this one. So we want to determine if they are enantiomers. Remember, if they are enantiomers, that means they are mirror images. So that means that if this one's R, then this has to be S for it to be an enantiomer. So this is the right-handed model. This has to be the left-handed model. So let's see if that's true. So there's two ways to do this problem. I'm going to show you the hard way first. So NH2, again, we only care about this carbon. This carbon is the stereocenter. This is the chiral center. We don't care about this one. So again, there needs to be 4 atoms bound that are not identical. So there's one nitrogen, methyl. Remember, there's a secret hydrogen over here. So you're always going to have a wedge, and I forget what this one's called, but you're going to have one that's pointing outward and one that's pointing backward. So that's how I know that this is a wedge, because this is the back one, so this has to be the wedge. And then we have this carbon here. Okay, so then we're going to rank it again. We know nitrogen has an atomic number of 7, so this will again be 1. We know that this is the lowest, must be 4. So then it's between these two again. So remember, this goes to carbon, then it's attached to 3 hydrogens, and this one's attached to 2 carbons. So carbon, hydrogen, carbon, 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 carbon wins. So this one's 2 and then this one's 3. All right, so same thing. I'm going to write this in a simpler form. So I'm just going to write the numbers. So 4, 1, 3. This is 2. Okay. So if you saw my rule before, 4 has to be in the back. So right here, this was really nice to us because 4 was already in the back, so I didn't have to do anything. Yeah, so the 4, the lowest, whatever the lowest rank substituent is, it has to be in the back. So this was already in the back, we were good. I could just determine the order. Here, as you can see, 4 is in the front, which sucks. Okay, so it's not in the back, it should be in the back. So what we have to do here is we have to actually turn or like rotate the molecule. So that seems a little confusing, but don't let it mess with you. So all we're going to do is we're going to pretend that I'm going to hold on to number 3. Okay, so I'm holding on to number 3 like a stick. And I'm going to physically rotate these ones. So I'm going to move 2. So I'm going to turn this whole molecule. So 2 will go over here. 1 will go over here. And 4 will go over here. Okay. So then what we're going to get is 3 is going to stay stagnant, right? Because I'm holding on to that part. 2 moves over here. And this, I drew that wrong. 2 is going to move over here. I know that looks weird, but that's going to be 2. And then 1 is going to move to the wedge. And then 4 is going to move here. Okay, so I want to move it again. So I'm going to move it again. So 4 is going to go over here. This one's 2. 2 is going to go over here to the wedge. And 1 is going to go over here. Alright, so then we get, so then this is going to look a lot easier. So 4 is in the back. 2 goes to the wedge. And then we have 1 here. Alright, there's 2. So then you just have to count it in order. So now this is the proper configuration because 4 is in the back now. So now I'm going to count 1, 2, 3, 4. So 1, 2, 3, 4. It is going counterclockwise, so this is S. Okay, this is S. This is R, so yes, they are enantiomers.